Next, there will be a presentation of the team Net Zero with the title Proposal for Amendments to IGF Code Considering Risks of Ammonia Fuel Focusing on CFD Modeling. Everyone, please welcome Team Net Zero.
Hello everyone, we are Team Net Zero. Our team name Net Zero illustrates the importance of decarbonization in maritime industry.
It's an absolute honor that we could share our thoughts.
We hope that it's going to be such a valuable time today. Thanks so much.
Honorable judges and esteemed colleagues, we are Team Net Zero. It's a great honor to present our proposal for amendments to IGF code, precisely considering the risk of ammonia as a marine fuel. So this is our agenda. We propose ammonia as a marine fuel in production and risk of ammonia and case studies CFD modeling. And the summary in conclusion. In 2023, IMO adopted a revised greenhouse gas strategy, setting a goal to achieve net zero. And European Union has introduced the Fit for 55 package. With the regulation becoming progressively stricter, eco-friendly fuels are no longer optional, but essential for the future of maritime industry. This timeline provides an overview of key regulations introduced in the maritime sector over the past decade. It highlights the major milestones such as EU ETS, EESI, and CII. This illustrates a potential decarbonization scenario in maritime industry. As we can see from the graph, oil-fueled vessels are represented by the red line, and the fuel oil will essentially be phased out. However, zero-carbon fuels shown by the blue line are expected to rise significantly, becoming a dominant fuel. Ladies and gentlemen, as a fuel oil is phased out, the alternative fuels are no longer optional, but essential, and we propose that the ideal solution is ammonia. So why ammonia? To answer this question, let's look at the infrastructure. Globally, ammonia production is already well established, with around 180 million tons of gray ammonia produced annually. This production is supported by a robust port infrastructure. Now let's look at the demand and price considerations for ammonia. The top two graphs illustrate the cost change in terms of blue and gray ammonia. As we can see, blue ammonia, shown by the blue line, tends to be more cost-effective. However, with rising CO2 fees, the production cost for gray ammonia, shown by the gray line, also increases, narrowing the gap between blue and gray ammonia in terms of cost. Now we move to the main section. Let's examine how ammonia behaves as a saturated liquid and the key management steps involved. This is a pressure entropy chart of ammonia. It shows how ammonia behaves in different circumstances. By understanding and following these management steps, we can effectively control vapor generation. Here we overview two main ship-to-ship ammonia bunkering methods. On the left, FR to FR and SR to SR, which stands for fully and semi, involve transferring ammonia at a lower temperature, which is requiring cooling and handling. On the right side, NR to NR, involve transferring ammonia at ambient temperature, which is eliminating pre-cooling and simplifying the process under the circumstances. So ammonia has notable safety risk due to its toxicity and flammability. So in terms of toxicity, ammonia can be detected by the smell at 5 ppm. Exposure levels are classified from AEGL 1 to 3. AEGL stands for Acute Exposure Guideline Level. At 30 ppm, discomfort or irritation may begin. It shows the risk threshold for ammonia bunkering. Regarding flammability, ammonia's flammability limit is 150,000 ppm, which is far above toxic levels. Therefore, ammonia can technically ignite, but the main risk is toxicity. At the 8th CCC convention, the use of ammonia as a marine fuel was discussed, and it highlights the need to establish guidelines based on risk assessment. In this context, CFD modeling is a great risk assessment method for understanding ammonia's behavior in various scenarios. And my esteemed colleague will now continue with CFD modeling and its relevant case studies.
Okay, so we will move on to our next section, CFD modeling as a countermeasure for ammonia risks. CFD modeling is the science of using computers to predict liquid and gas flows based on the governing equations of conservation of mass, momentum, and energy. CFD modeling analyzes different properties of fluid flow, such as temperature, pressure, velocity, and density, and can be applied to a broad range of engineering problems across industries. In the next slide, we're looking at CFD modeling-based scenario tool, PHAST. Use of PHAST can simulate ammonia release and dispersion scenarios. Starting with the source model, PHAST characterizes the release process taking into account factors like the material's release rate, total quantity, physical state, and temperature. For passive dispersion, we use models like Gaussian diffusion and Pascal G4 to predict ammonia dispersion in the atmosphere, considering turbulence and atmospheric conditions. And this is a sensitivity analysis of an ammonia leak. It is possible to set up different operational parameters and weather parameters for simulating. Scenario A, B, C shows how results change when different parameters are applied. This is a sensitivity analysis of ammonia risk leak. It is possible to set up different operational parameters and weather parameters for simulating. Scenario A, B, C shows how results change when different parameters are applied. Scenario A. In this scenario, we assume an 8-inch hose rupture at the inlet manifold of the receiving vessel lasting for 60 seconds. Scenario B. Here, the storage conditions are simulated back based on a 5-minute release from a valve attached to a storage tank. Scenario C. This scenario involves a 225 millimeter leak from a 10,000 cubic meter atmospheric storage tank occurring at a height of 3 meters above ground and lasting for an hour. For each scenario, parameters like storage temperature and pressure, flow rate, and release elevation and duration influence lethality footprint. Like these scenarios, CFD modeling can simulate different scenarios of ammonia diffusion. This is case study of ammonia release during a ship-to-ship bunkering operation. The chart in the left is showing different parameter setting for simulation. The graphs on the right illustrate ammonia concentration dispersion at 2, 5, and 10 minutes after the release. The colors indicate different ammonia concentration levels based on AEGL for day and night, with 220 ppm and 2,700 ppm represented in both day and night conditions. This case study builds on our previous ship-to-ship bunkering case by analyzing the lethality footprint of an ammonia release. With appropriate mitigation measures, we can significantly reduce these lethality footprints, especially for areas closer to the release source. It is also effective for simulating range of ammonia diffusion. This lethality footprint analysis highlights the importance of time of day considerations and mitigation strategies in planning for ammonia bunkering safety. This is another case study at Gamman Wharf, simulating diffusion of ammonia using CFD modeling under condition of summer southward winds at 20 knots. The results revealed that under strong southward winds, ammonia tends to disperse quickly across a wide sea. My esteemed colleague will now continue with amendments of IGF code.
Next, let's look at our proposed amendment to the IGF code. The IGF code, part of the SOLAS Convention, sets safety standards for ships using low flashpoint fuels, like LNG and potentially ammonia, to ensure safe operations at sea. The IGF code currently focuses on LNG as a fuel, but we propose adding ammonia. Ammonia has unique risks, so we recommend using a simulation-based risk assessment to study how it spreads, especially in worst-case scenarios. This approach will allow us to predict how factors like wind and temperature might impact ammonia leaks. With this information, we can put the right safety measures in place. First, we propose amendment to section 2.2, where there are currently no clear definitions for ammonia as a fuel or for simulation-based risk assessment. We suggest adding defining ammonia fuel as anhydrous ammonia used as ship fuel, and introducing simulation-based risk assessment as a computer modeling method for safety analysis. These additions will clarify safety regulations and help ensure consistency in ammonia fuel ship operations. The next amendment focuses on section 4.2, where simulation-based risk assessment is not currently required. We propose that ammonia fuel ships perform this assessment 48 hours before arriving at port for bunkering. To support this, port should provide weather data, and each ship would be equipped to send this assessment to port authority. This coordinated approach will enhance preparedness and improve port coordination. Also, ships should use simulation-based risk assessment to evaluate potential leak scenario, taking into account different weather and ship operating conditions. This would include identifying toxic zones, assessing impacts on crew safety, and evaluating ventilation systems, and a mitigation strategy. This amendment aims to enhance safety and ensure ships are well prepared for ammonia-related risk. Now, focusing on bunkering operations in section 8.3.1. Currently, there are no standards for stopping bunkering in case of ammonia leaks. We propose that bunkering be immediately halted if ammonia levels of 30 ppm or higher are detected by gas detectors. This level provides a safety threshold, allowing quick response to prevent leaks. Finally, for section 15.8.1, there is currently no requirement for gas detectors in areas with high crew presence. Given ammonia toxicity, we propose mandatory installation of detectors in halls, void space, living quarter, and the other potentially hazardous areas. Next, conclusion. To conclude, our proposed amendment of the IGF code aim to address the unique safety and environmental challenge posed by ammonia as a marine fuel. These amendments align with IMO strategic direction 2, specifically performance indicator 2.3, which focus on updating the IGF code and establishing guidelines for alternative fuels. We request that this proposal be direct to MSC and further-reviewed by SSE. Thank you for your attention.
Thank you, Net Zero, for impressive presentation. Okay, we will take a Q&A session. Can we take questions from the judges? Okay, Dr. Gang, please.
Thank you. It's very interesting and timely presentation. Especially this topic is very very hot issue. Especially as you know, the IMO now discussing the safety of these kinds of new alternative fuel, including ammonia and hydrogen, others. I'm not sure. As you mentioned, this issue, especially regarding the safety of this ammonia and other hydrogen, other alternative fuel, are being discussed at MSC, CCC, of course, including that other committee. But recently, as far as I remember, last September, the IMO, MSC, CCC 10th meetings conclude, and they developed these kinds of some, of course, differently related with the IGC code. Draft version has been finalized and submitted to the next MSC. And then they are proposed some the future work to ensure the safety this ammonia, especially to use a new alternative fuel as ship. Had you ever compare your result or suggestion with already made some conclusions made at IMO, MSC, CCC? My second question. It's just a small comment, but not to you or but also. I'm not sure you had ever showed a lot of figures and some tables included, which including some data or some information. But have you ever made them by yourselves or refer to other documentation or some sources? When you use such kinds of other sources reference, you needed to refer that some sources at each slide when you present. There's a small comment. Thank you.
Yeah, thank you for your thoughtful question. And first of all, to answer your last question, yeah, we recognize that we need to put each references on each slide, but yeah, sorry for the excuse that we have a lack of the space, so that we just put all into the last slide, all the references on the last slide together. And as you mentioned, the current CCC convention was discussed these kind of things that so yeah, we also recognize that so actually eventually why we include this kind of topic to IGF code, which is because IGF code stands for International Code of Safety for ships using gases or other lower flashpoint fuels. So IGF code is comprehensively addresses safety regulations for vessel using low flashpoint fuels. So currently IGF code mainly addresses existing low flashpoint fuels like LNG, but just only mainly they address only LNG. So that's the reason why we brought up this kind of conversation that IMO should also address in the IGF code.
Yeah, may I add one comment? already the IGC code has has been revised by the last MSC CCC meeting, especially regarding the safety of ammonia as a course of cargo. So you need to compare some the safety issue which has been made at their meetings with viewers. Thank you.
Thank you so much. Do you have any comments about the question?
Yeah,
or
thank you for
comments?
insightful question. Yeah.
Okay. Can I get more questions from judges? Okay, let's move on to the floor. Any questions about this presentation? I think Team Appada and Team Big Wave and Team IMO Solution, 3 teams have more chance to ask questions. Okay, Team IMO Solution, please.
First, thank you for your interesting proposal. I want to ask that the basis for proposing the criterion to stop bunkering at 30 ppm has been suggested. Could you explain the rationale for setting this concentration and how it compares to other standards? Thank you.
Thank you for your wonderful question. The 30 ppm is correspond to AEGL 1 level. This means the concentration about initial discomfort or irritation from ammonia exposure begins. Stopping bunkering this level enables quick identifications and response to early hazards. Also, 30 ppm is adopted common standards in various industries. So, it is a critical point for maintaining safe environments. Thank you.
Thank you. And are there any questions on the floor? Okay. Yes, Team Safe System.
Thank you for your presentation. And I have a question that data collection and maintenance costs for CFD modeling are likely substantial. So how do you assess the cost effectiveness on this approach? Thank you.
Okay. So although there may be initial costs, predicting risks in advance with CFD modeling is highly beneficial for preventing potential accidents and reducing response costs. Additionally, computers for CFD modeling can be installed on each vessel, costing around $7,000 per unit. Moreover, in the long term, it reduces financial and human losses from safety incidents, and its cost effectiveness has been proven across various industries.
Thank you. Can you get more questions from judges? Yes, please.
Okay, thank you for your presentations. I never seen until now in reality the ammonia ship-to-ship bunkering. And so, simple question: do you have any example and to the commercial vessel, the ship-to-ship bunkering of ammonia? That is one question. And so, what is the difference between the bunkering condition between the conventional vessel and to the ammonia vessel? What is the different conditions, bunkering condition? That is the second question. Could you explain that?
So your second question means why different factors affect during ammonia bunkering, right?
Yeah, because of to the condition, the bunkering condition. What is the difference between the conventional vessel, the HF fuel oil, and another to the gaseous fuel oil, in particular, to the ammonia fuel oil bunkering condition?
The reason why
Yeah.
it is important for ammonia is because of its toxicity, and when it leaks, and it can affect humans. And as we showed in the slide, the pressure enthalpy chart of ammonia, it shows that ammonia reacts in a broad range in different conditions.
And on top of that, that's the reason why we brought up those kind of amendments, such as like during the bunkering process, if the ammonia leaks, then the gas detector detects over 30 ppm or so on, then the bunkering should be suspended immediately. And we also suggested that gas detectors shall be installed such places like hold, void space, living quarters, or any other potential hazardous areas. Yeah, that's the reason why we brought this kind of amendment. Yeah,
I got it. I understand to what you are saying. And then to the first questions, could you introduce to some example?
So the first question was you asking us that if there is any example of ship-to-ship bunkering of commercial ship-to-ship bunkering of ammonia as a marine fuel, right?
Yeah.
I think there is some commercial ship-to-ship bunkering now, but as we are making the slide, we focused on CFD modeling as a countermeasure of ammonia leak. So we just came up with a scenario, and it is a scenario of a bunker vessel and a container vessel. So I think that can kind of answer to your question.
Yes, I have never seen to the ship-to-ship the ammonia bunkering. So I would like to listen to some cases. For example, the shipping companies to to carry out to the bunkering.
Yeah, we fully understand the full question. Actually, ammonia fuel oil hasn't been commercialized, so that there is no case like that. But the reason why we brought this kind of procession is that the other fuel oils, such as LNG or such as things like that, fuel oil is bunkering like for this kind of procession. So yeah, that's the reason why.
Okay, thank you.
Thank you. I would love to spend more time on this Q&A session, but the time is up, so it's time to end this Q&A session. Thanks all judges for your insightful comments and questions, and participants as well. Let's give them a big round of applause.